start. So, good morning, everyone. Welcome to the beginning of the second round of lectures of the theoretical and computational part of the summer school. And this morning, as you know, Dr. Charles Crosby will continue with his second lecture on computational fluid dynamics. Yeah, and I would like to thank also Andrew because he volunteered to keep an eye on the chat and on the Q&A. Yeah, but if you want, you know, since it's a seminar format and you have something very urgent, nobody will stop you from asking a question in between. Yeah. So please, Charles, it's your show. So if you want to start sharing the screen or start, we are looking forward to the second lecture in your series. Thank you very much.
Thank you, Francesco. Righto. Well, welcome back. We'll pick up more or less where we were on Monday. As we handled it on Monday, I'm very keen on the idea of getting as much interaction going with the class as we can. In other words, we will, after each segment, and once again, we'll divide this lecture up into 3, possibly 4 shortish segments. And I'm quite keen that after each segment, we have an informal chat about what we've just talked about. And if there's anything that's unclear still, that we can try and clarify it. And then also, if there's anything you might want to question at any stage that you want to write in the chat box, please do so. And also, if there's something that happens during the lecture part that you'd like to ask about, please proceed and do so, because it brings a bit more life to the approach, and it gives me a better idea of whether the lecture is getting close to hitting its target. As I explained on Monday, this is not a course based on fundamental theory, and I think it's quite important to distinguish why we're doing it this way. If you are going to be working in the development of CFD methods, or using CFD methods in the analysis of very complicated situations, in other words, where precision, accuracy, new models and things are really important, then there's no simple way to go about learning how to do CFD. You've got to start from the absolutely fundamental theory of fluid dynamics. You've got to start with fluid dynamics theory, and then you've got to get really deep into the theory of the methods, because everything builds on that. If you don't have that basis of a sound theoretical knowledge of where all this is coming from and what it's based on, then you are going to be having quite a bit of difficulty further down the line, because what you don't master at this stage is going to trip you up later. On the other hand, if you're going to be working in a more superficial way with it, let's say more of an engineering way, perhaps less of a research approach to using computational fluid dynamics, then probably it's not so important to get all the fundamental theory of the numerics and the mathematics of CFD established. What you do need to get done is to establish a very firm foundation in fluid dynamics, because fluid dynamics is complicated. There's lots and lots of unexpected things that happen when you start dealing with fluids. And the only way you can reliably use these techniques in practice is if you actually have that very solid foundation. Having said all that, teaching those fundamentals is the task of the university. The objective of this particular course is to expose you to the kind of things that you need to go away and learn. So we're doing this fairly superficially. Just give me a moment. I need to shut up a cell phone, which is bothering us here. Sorry about that. Righto. So let's get into the lecture then. Today's lecture is basically split into 3 parts as before. If we find that we're going fairly fast, we can get into the first part of what I intended to cover on Friday. The first part here is about the mathematics and numerics of CFD. Now, this is incredibly superficial, because if you did it properly, we'd be busy for the rest of the year. The second part of the lecture will be about turbulence. It seems maybe a little bit strange to start talking about turbulence before we talked about the intrinsics of CFD that much. But in fact, it's turbulence to a large extent that makes fluid dynamics complicated. So you've got to understand at least where that comes from. And then in the third part, we'll get into more detail on what's involved with the CFD again. Right, so this particular micro lecture, I'm assuming you can see that, is about the mathematics and numerics of CFD. Right, so the Navier-Stokes equations govern CFD. These equations were derived back in the 19th century, and it's basically a set of conservation equations. They express conservation of a number of properties. First of all, preservation of conservation of mass, then conservation of momentum, conservation of energy, and then conservation of other properties, which could be things like chemical species. So I used to do with my aerodynamics students at university, I at least used to take them in great detail through the derivation of the equation of continuity, which expresses conservation of mass. The reason for doing this is because it's a nice, easy derivation to do, and it's easy to follow, but it establishes a principle that you would use to work with these equations in general. The equations of momentum, which is really what we normally refer to as the Navier-Stokes equations. These are the ones that give you the velocity and pressure. Effectively, you're applying Newton's second law there. We'll talk a bit more about that in a moment. And then your other conservation equations. If you're dealing with flows with variable energy, in other words, compressible flows where the speeds are fairly high, or anything that causes the density to change or the internal energy to change, then you need to apply conservation of energy as well. And then, of course, if you're dealing with reacting flows, then you've got quite a lot more to add. All of these get expressed in similar equations, which we refer to as transport equations. You should be familiar with this general approach. If you're deriving partial differential equations, you start off with a small volume, incremental volume dx by dy by dz, and you basically do an algebraic sum of what's going on that infinitesimal volume. If you're only dealing with continuity, then it's quite simple. The mass which goes in must be equal to the mass which leaves minus what gets left behind. So it's a simple algebraic sum. That gets you your continuity equation after you've done all the operations on it. If you're going to derive momentum equations, then you're effectively applying Newton's second law, but you're doing it to a small moving parcel of fluid. So strictly speaking, you wouldn't express it as force equals mass times acceleration. It comes down to the sum of applied forces must be equal to the rate of change of momentum. F equals ma is the convenient shorthand, but that's not exactly what we're dealing with. It's actually a rate of change of momentum. So we're dealing with conservation of momentum here. And you work with the fluxes on each of these faces, and then what happens inside the volume. So once again, your sum of your applied forces would be external forces. That would typically be things like gravity or electromagnetism. And then we have pressure forces. We've got a pressure gradient across this parcel of fluid, which would cause it to accelerate. And that's accounted for on the faces of the control volume, or this infinitesimal volume. And then we've got shear stresses along these various faces. So you add all that lot together, do your conservation of momentum, and then you end up with the Navier-Stokes equations. I'm not going to do the derivation because once again, we'll be busy here for the rest of the day. There's an important thing to remember here, though, is that we're dealing here with an infinitesimal small volume. And when you're dealing with finite methods, like the finite volume method to describe computational fluid dynamics, you are going to be working with volumes a lot. Essentially, you take the same approach and you scale it up to small but physically sized volumes in a grid, so-called grid cells. And effectively, you apply this process in reverse. You could actually just use the pressure gradients and the shear stresses as they are, but it's much more convenient to work with it in the form of a differential equation. But this process effectively scales up. So you use it in the derivation of your equations, and then you use it in the development of your finite method, be that a finite difference method, a finite element method, or a finite volume method. And then it goes one step further, because when you start dealing with parallelized methods, which is in high performance computing exactly what we do, you start lumping together these volumes so that you've got collections of small volumes. And in fact, when you start solving the equations of those on those groups of volumes, those basically the decomposed flow domain, then you could typically use an algebraic multigrid method, where you're once again agglomerating a number of these volumes to do the solution of your equations. So think in terms of hierarchies of small volumes, starting from infinitesimal and ending up to very large. Right, so this is one way of expressing the Navier-Stokes equations. This is a very longhand way of expressing it, but it is useful because if you're going to be programming it from scratch, this is where you would start, and actually you would start with a discrete form of this. Although you've got a lot of terms there, you've got 4 separate equations, 1 continuity equation, you can remember conservation of mass, and then three momentum equations. They have been somewhat simplified, and there are 2 important simplifications that have been made. And the first important simplification is the density is constant. This is incompressible flow. And this is a very big assumption, because we know when we're dealing with gases are very much compressible. The density does change, and the density changes with pressure, and the density changes with temperature as well. But if we're not applying any fluxes of energy, we can disregard the changes in temperature, if provided that the velocities are low enough. With liquids, your assumption of a constant density is more valid, except when the temperature starts changing, and then you do need to account for the changes in density. But if we're assuming that the density is constant, then the density ends up outside of this term that's in brackets here. If it was variable, it would become the group together with the velocity vector component in the partial derivative. So that's one important assumption that gives us this as a much simplified form of the equation already. And then the second one is the expression of the shear stresses in terms of the molecular viscosity, which we're also assuming is constant. Once again, molecular viscosity is not constant. It does change with properties, and most importantly, it can change dramatically with temperature. Certain substances, for example, oils, the viscosity is very, very strongly dependent on temperature. So it's not always a good assumption that the viscosity is constant. How did we get from the momentum equations, or from the expression of the conservation of momentum on the infinitesimal volume, to this equation with just the viscosity? This is done by way of Stokes' hypothesis, because normally you would expect, if you just followed the derivation, you'd be expressing this in terms of shear stresses, or shear stress tensor, strictly speaking. And only then do you bring in via Stokes' hypothesis, which is something that's experimentally calibrated, shall we say, the relationship between the molecular velocity and the shear stresses. Nevertheless, if we assume the viscosity is constant, then this term on the right-hand side becomes a lot simpler. At least this is not non-linear like the terms on the left-hand side. We've got, for example, here, the velocity multiplied by the derivative of the viscosity, which immediately makes this a non-linear equation. In general, actually, we find that we have to follow a slightly different approach when we're dealing with real flows, because the way of handling turbulence involves messing around with the viscosity, and then it stops being constant as well. We'll get onto that in the next lecture. So 4 terms essentially visible in this equation. There's the pressure gradient, which is easy to visualize. If you've got a pressure gradient, it's easy to imagine that it's exerting a force on that volume. There's gravity, which may or may not be present. If the gravity vector is constant, we don't have to, and the density is constant, we don't have to worry about that effect, and we can drop it. If there were other externally applied forces like electromagnetic forces, they would have to be grouped together into this in the source term here. Right. We refer to this as these 3 terms as the convection terms. It's not immediately obvious the way it's expressed with velocities, but that represents the amount of momentum that's transferred by the motion of the fluid itself. This is the transient term, the derivative of time. And if we've got, if we take the special case of steady flow, we can just simply drop that term. And this is the diffusion term, which is due to molecular viscosity in this case, and that's your pressure gradient term. Right, so that's a much simplified version of the equation. This has got a lot more to it. It looks simpler because it's been expressed in essentially shorthand vector notation, but this is a more comprehensive version of the equation because it now takes into account, first of all, that the density may vary, and it's not making, in this case, assumptions about the diffusion coefficient, which is the viscosity when we're dealing with momentum. But this is a general form, and this is what we call a transport equation. Because you can take your four terms, and they're clearly visible in this form. You have a transient term, you've got a convection term, a diffusion term, and a source term. But now we need no longer think of it in terms of necessarily momentum. You can think here also in terms of this being some kind of other property. It can be a scalar or a vector. We're just using the expression phi as a variable in this equation. Transient, convection, diffusion, and then a source term. Think for a moment what these mean. This expression, the transient term, describes the rate of increase of the property inside this fluid element. So it's something that happens to the volume of that fluid element. This is the rate of increase due to sources, be some kind of chemical reaction. It could be gravity, it could be electromagnetic force or something like that. Once again, it's acting on the volume of this infinitesimal volume. But then you've got these two terms, which is basically how much of the property flows in and out. This could be momentum, this could be energy, it doesn't matter. And this is the way that it's diffused. Now, these two terms are best described not on the volume of the controls of this control surface, but on the control volume, but on the surface. So you've got a single equation which deals with both the volume and the of the control volume and its outer surface. So it's best expressed in integral form, which is how you use it in the finite volume method. So if you integrate it, it makes sense that you take the transient term and you integrate it over the volume of this control volume. Likewise, the source term, because it's a volume property, you integrate it over the volume. But the surface fluxes are a little bit more awkward to handle. They're not really, it doesn't make sense to integrate them over the volume. You would much prefer to integrate them over the surface. And this is where Green's theorem comes in. Green's theorem is a very useful expression, which theory that you find used in various forms of fluid dynamics, because it gets you away from having to deal with a volume integral when you're talking about a property that's not really a volume property. So working with the normal vector on the surface of the control volume, the dot product with the quantity that we're dealing with, then we can start working with with just a surface integral. So it makes it a much more a form of the equation that's much more easily handled. So two volume integrals and two surface integrals. Right, to summarize what we've talked about here, got a system of equations, so there's no single Navier-Stokes equation. You've got a system of, always got a system of equations that you need to solve, and you need to find some kind of way of solving them together. You can solve them together in one matrix, or you can solve them sequentially. That's got fairly important implications. Especially on the convective side, there's very significant nonlinear terms, so you're always going to be stuck with some form of iterative method to solve them. And then quite importantly, the equations as expressed here are universal, provided you're not making special assumptions about incompressible or constant viscosity or those. If you take them in the form expressed in the previous slide, they hold for all these flows. And importantly, they work for steady flow, they work for transient flow, and they work for laminar and turbulent flow. So we'll talk a little bit in this next short lecture about exactly what happens with transient and turbulent flows. And it turns out this is the kind of thing that makes fluid dynamics a little bit awkward. is because we have to deal with the difference between what you'd expect to see from a steady state or a gradually varying solution and something that varies at a very small scale instantaneously, which is what we call nearly instantaneously, which is what we call turbulence. And that's essentially an insolvable problem. There are ways of using the Navier-Stokes equations to solve directly for the small scale fluctuations involved in turbulence. But that's very, very, very demanding. And it only finds application where you've got very powerful supercomputers and you're applying it to very small research problems where you're trying to understand the fundamental nature of what's happening. You can't really apply it to analysis of real world situations because it's just an impossibly large mathematical problem or numerical problem. Of course, we always say, we say impossible, it's impossible today. It may very well not be impossible in 10 years or in 20 years. It may become more practical in 10 years or 20 years. But unfortunately, turbulence is a problem and we have to find ways of dealing with it. Fortunately, we found ways of dealing with it, but they do come with approximations. There are lots and lots of peculiarities of CFD, which we'll deal with in the third part of today's lectures. But one of them immediately pops up when you look at these equations. Let's just go back to this slide. This is simplified, but it illustrates the problem very clearly. Basically, assuming that your viscosity and your density and your gravity and all that are known, you've got four equations. You've got four equations and four unknowns. So your four unknowns are your three velocity vector components, u, v, and w. And your fourth variable is the pressure P. And conveniently, we've got four equations. So fundamentally, we've got a closed system. We should be able to solve this lot. The problem is we've got an equation for u here. See, it's du, du, du. So this is the equation for u. This is the equation for v, the y direction velocity, dv, dv, dv. And w, we've got an equation for. And then we've got a fourth equation, but the pressure doesn't show up in that equation. So this gets us the concept of pressure-coupled equations. We absolutely need to solve the pressure, but we don't have a convenient equation which is going to solve the pressure for us. And this was quite a major showstopper in the early development of fluid dynamics. The problem goes away when the flow becomes compressible because then density starts showing up in that equation and you can couple through the temperature and the energy, you can find the pressure. But if you're dealing with incompressible flows, which is where these methods started, you've got a fundamental problem that you don't have an equation for the pressure. You've got to kind of find some kind of way of introducing it in there. We'll talk a bit about that in some of the later lectures. So that is the question of the pressure not involved in the continuity equation. And I've now basically given you a special case of a general transport equation. Right, so yeah, which is the Navier-Stokes equations, but you'll find that a lot of other things in the field of CFD start falling into the shape of a general transport equation. Right, so that's it for this part of the lecture. Questions at this stage? Nobody? Should I pick a name at random and ask a question of that person? No, we're not going to do that.
I just wanted to say that is a brilliant idea.
I think that's not. I won't do that. I won't be that unkind.
Okay. We won't be mean.
Well, maybe we should be mean, but no, we won't be mean for now. Okay. If there are no further questions, let's get on to the second part of the lecture. All right, is that clearly visible? Starting to sound like an optician. Righto, I'm assuming that everybody can see this lecture 2.2 on turbulence. Right, I had to argue a little bit with myself about whether or not one should introduce turbulence into this series of lecture and whether it needs to come in once or twice. because I've already alluded to the fact in this previous part of the lecture that turbulence is inherently one of the things that makes CFD rather difficult. So it's easy to start talking about turbulence instead of turbulence, because it really is a special thing which you don't really have an equivalent of in a lot of other computational domains. Right, so talking about it in theory, basically unsteady Navier-Stokes equations would be applicable to the rapid fluctuations in turbulent flow. You still got conservation of momentum, you still got conservation of energy. So those Navier-Stokes methods work also for basically the Navier-Stokes equations. If you can get down to the kind of scales that you need to, will resolve turbulent flow. So you've got to stop for a moment and think a little bit of about what you see when you've got turbulent flow. And it's best described as small-scale rapid fluctuations on a mean velocity or conditions that are also changing with time. You have to assume that the turbulence is an order of magnitude or so smaller than the mean values, because if it's of similar magnitude, it's more accurate to describe it really as an extremely unsteady flow. There's no hard boundary when something goes away from being unsteady to becoming turbulent, but in practice, it's pretty obvious when you're dealing with turbulent flow, and in fact, your flows are mostly unsteady as well. In other words, your mean conditions are gradually changing as well. I've got the good fortune of living in Cape Town, and I've discovered that there are quite a lot of ways here that you can see turbulent flow in action. And it's quite instructive to actually see this. In autumn, we still get very strong winds. Basically, Cape Town gets very strong winds more or less all year round, but particularly in summer. But towards late summer, early autumn, when all vegetation is very dry, you get a lot of seeds that get dispersed by the wind. And these seeds are very light, and they've got the advantage of acting like a very simple form of flow visualization. So you can see what the airflow is doing while you're driving along in the traffic in this wind. And we are talking really about quite extreme levels of wind here. And you'd expect to see particles flying past your car in more or less horizontal direction. And it's quite interesting to see that this is exactly what they don't do. These particles do not travel in straight lines. They travel on random paths as they move with the turbulent structure of the wind. So the wind has got a strength of, for argument's sake, 15 meters per second. And there's some additional fluctuation on top of that, which could be 1, 2, 3, 4, 5, probably not more than that, meters per second as short-term fractions of second fluctuations. At this scale, you can clearly see the motions. You can see the path of these seeds, and you can see them swirling in all kind of directions. So if you scale that down, then you can start thinking of how you would model it with the Navier-Stokes equations. So the field of directly using the Navier-Stokes in the essentially primitive form to study turbulence is called direct numerical simulation. So we all love acronyms. So this is DNS, direct numerical simulation. It depends quite strongly on the Reynolds number, the ratio between momentum and viscosity. But in general, a rule of thumb would be that you would need approximately 100,000 grid points to resolve a cubic centimeter of flow. That's dramatic. 100,000 grid points in CFD these days is not that much. We easily go to 100 million, which is basically 3 orders of magnitude more. But that would only give you 1,000 cubic centimeters of fluid. In other words, a liter bottle of milk. So you can resolve the turbulence flow in a volume of fluid, which is roughly the equivalent of a bottle of milk or soft drink or water, whatever your favorite drink is. And that doesn't get us very far in real life, but it is enough to start studying fundamental properties of turbulence. For everything else, we have to use turbulence modeling. So turbulence modeling allows us to express the effect of turbulence without expressing the turbulence itself. So we don't have to have a grid that's so fine that we can resolve the turbulent eddies, but we need some way of expressing what the average effect would be of these turbulent eddies. So there are very many approaches, and they use different levels of complexity. An early approximation was developed by the guy who originally developed the boundary layer theory, Prandtl, with a mixing length hypothesis, which is a way that you are saying that you could express the mixing effect of turbulence on the basis of a length scale. And by then coupling that length scale to a effective turbulent viscosity, you could find some way of expressing the effect of turbulence on a subgrid scale. So turbulence modeling has basically grown from that approach. So you would typically solve some transport equations to find an expression for that turbulent viscosity, that effective turbulence viscosity. And yeah, many different levels of complexity. One of the first ones you'd encounter would be a so-called zero equation model, which sounds silly because when you look at it, it's got some quite complicated equations involved in it. But these are local equations, they're not transport equations. So you're effectively only considering the gradients in the flow at a point. And you would couple that then with a mixing length, and from there, a eddy viscosity or a turbulent viscosity. So one of the better known models of that nature is the Baldwin-Lomax model. I haven't seen anybody use the Baldwin-Lomax model for a long time because it's a very simple model, and there's quite a lot that it doesn't do, but it was initially in the early stages of turbulence modeling quite widely used because there wasn't anything really else. And then you can move into more complexity, where you actually introduce transport equations for the turbulence. So where you can, and here you can now allow turbulence to move. You can get it, you can transport the turbulent kinetic energy or the effect of the turbulence from one part of the fluid to another, and you can allow it to dissipate. And you can start adding more and more transport equations to make the physics more and more closely resemble experimental conditions, real life. So you'll find in real life people are kind of standardized largely on two equation transport models. There are certain one equation transport models that do a really good job. There's no universal turbulence model. And this is the thing that you have to learn if you're dealing with CFD. The different turbulence modeling approaches are best suited to different types of flows. And good practice is to start simple, like everything else in computational or any other science. Start simply, and you find something that will give you the simplest possible method that will give you answers that are of use to you. Right, so what does turbulence look like? This is an absolutely classic standard kind of test case in CFD is the backward facing step. One of the first things you do when you start learning CFD after you've done a simple flow in a duct or a channel or a pipe is you start dealing with a sudden expansion of the flow path, a backward facing step. You can go and experience it yourself. You go and stand on the downwind side of a building, you'll feel an effect that's quite similar to a backward facing step. And one of the things that you're probably not going to experience is totally calm conditions on the downwind side of that building. And the reason for that is that the flow swirls over that corner and into this region. In reality, it does this in a very complex way with eddies of fluid of different size and intensity and velocity. If you take a long-term average of it, you get this. You get this region of recirculating low energy flow, which gradually mixes into the free stream conditions again. So this is what a nice CFD solution looks like, but it is nothing like reality. Reality doesn't look like this. And it's quite interesting to then take the next step, which is to see what happens as you go into this corner, because first of all, you're going to find on average a nice recirculating region here. When you zoom in on this part, you're going to find a vortex going the other way. And actually, if you zoom in some more, you'll find some more vortices that go the other way. And if you go in further, you find some more vortices that go the other way. It depends on how much you resolve that and what kind of modeling approach you follow. The main thing is That's more or less what it looks like in real life, if you could color the fluid according to its velocity. On average, that is the effect of it, and this solution is easy to get. So what are you interested in as analysts? Do you need to know that? In other words, do you need to know how rapidly these things fluctuate? Or is it good enough for your purposes to know what the average effect is? And that's a lot of what the science of turbulence modeling is about. What do you need the results for? You always have to remember that what you're modeling with a turbulence model is not physically realistic. It's the time averaged effect of something which is far more complex. And I think this is one of the other nice ways of demonstrating it is what happens to a smoke plume. If you take a high-speed photograph of a smoke plume with a flashlight or something like that, and high-speed film, high-speed sensor, sensitive sensor in a digital camera, then you'll see the structure in this turbulent flow. And the more you zoom into it, the more finer detail you will find. There's lots of little eddies and vortices and things. If you, by contrast, leave the camera with a shutter open and a low sensitivity of the sensor, then you will get this average effect. So you've got an effect of all these little fluctuations, which smears effectively out like that. So yeah, that's the effect of turbulence modeling. That's what the turbulence really looks like. I just want to take a look at, I see there's been quite a bit of conversation in the chat box.
Sorry, there was a question that came in late about which parts of the equation were affected in incompressible and compressible flow. I tried to answer it. I hope I haven't made too much of a mess of it. It was basically just expand.
Yeah. So I think that's a good answer to it. There's a little bit of magic to the Mach number of 0.3. Let's leave aside flows where you've actually got explicit transfers of energy due to something that's putting heat into it, for example, because that changes things and makes it compressible anyway. If you take the flow of a gas and you only take the compressibility that's a consequence of the speed into account, then the Mach number of 0.3 is actually quite a nice threshold. It's not a hard threshold, and it's related to the effect of the compressibility being 5%. There's a lot we're not covering, of course, in these lectures, but in the early days of fluid dynamics, applied fluid dynamics, when it came down to the design of aircraft, scientists became very good at finding simplified forms of the Navier-Stokes or other fluid dynamics equations to use for practical purposes. And it turned out that if you discard a lot of the effects that should not be present on a well-designed aircraft. So this is the trick with aircraft. They're nice and smooth and streamlined. So they don't do like backward-facing steps. You don't have many regions on an aircraft that look like that because they're nice and streamlined, because they have to be nice and streamlined. Turns out you can simplify the equations a lot. And then you end up with an equation that can give you nice, fairly accurate pressure distributions over aircraft type geometries for incompressible flow. And then if you assume that the disturbances are very small, the disturbances normal to the flow, mean flow direction are very small, you can come up with a compressibility correction factor, which is the square root of an expression which is 1 minus the Mach number squared. And if you were to set yourself a threshold of that compressibility factor being effectively a change of 5%, then you end up that the Mach number that gives you that is 0.3. So we like to use Mach 0.3 as a threshold of incompressible flow, because anything more than a Mach number of 0.3 is going to give you more than 5% of compressibility effects. So it's not a hard threshold, of course. In other words, if 2% compressibility is important to you for some reason, then it's actually technically compressible at a lower Mach number. In practice, you don't even need to go necessarily to a 5% threshold. You could go to a larger threshold of compressibility for most practical purposes, and then the flows, you don't need to take too many compressibility effects into account until you actually start encountering shock waves in the flow, and then the whole thing breaks down. This simplified expression had a side effect, which was that it goes to infinite it goes to exactly to infinite at Mach 1. So nothing can go exactly to infinite, but it goes to infinite at exactly Mach number of 1, which would give you the idea that the forces would be infinite at a Mach number of 1, which ties in nicely with the idea of the mythical sound barrier. Of course, in practice, you made the assumption of small disturbances when you derived that equation anyway. So by the time you get close to Mach 1, the disturbances are not small anymore anyway. So that expression is no longer valid. So there's no hard sound barrier, as we know. Right, to move back to these lectures. Right, the approaches that you can follow with turbulence modeling. For low Reynolds number flows, in effect, where the speed is small, the density is small, the sizes are small, but the viscosity is large, then laminar flow is a really good assumption. So all that the Reynolds number basically does is expresses a relationship between the inertial effects and the viscous effects. In other words, that which disturbs the flow divided by that which damps out those disturbances. So at low Reynolds number, disturbances damp out, and the flow really is laminar. So there are quite a lot of real-world situations where laminar flows are important. And it turns out that it can be a bit awkward because sometimes you don't want laminar flow. If you want chemical mixing, for example, if you're trying to mix things, you really don't want laminar flow. But if you've got small devices, you tend to get laminar flow. Airfoils at small scales, typically model aircraft, some kind of fans and things, also end up with laminar flow, and it turns out that there's some issues with laminar flows which make them quite difficult to deal with. So you'd actually rather prefer to have turbulent flow. From a simulation point of view, laminar assumption is nice because you can use the laminar form of the equations. You don't have to worry about turbulence modeling. So there are many real-world cases where you're dealing especially with small devices and low velocities where the laminar assumption is valid, and you should not use a turbulence model because the turbulence model is going to be inaccurate. And the turbulence model may not be accurate enough to effectively die off at laminar conditions. So then you should be using a laminar assumption. A good turbulence model will do that automatically. It will decay the turbulence to the point that the flow is effectively laminar. Right, dealing with the turbulent mixing is best done by deriving a form of the equations which we call the RANS equations, the Reynolds averaged Navier-Stokes equations. So basically, you're using the assumption that turbulent viscosities are small, turbulent disturbances, turbulence variations, are small perturbations on a slowly varying mean. And by small, we mean an order of magnitude or so smaller. So you've got the option with your derivation of your equations to now substitute your velocity terms and your pressure terms with a mean term combined with a perturbation term. So you substitute all those expressions in, do all the arithmetic that leads from that, and then you do the usual thing with the derivation of equations when you've got the product of small numbers of disturbances. You can assume that they're an order of magnitude or more or less important than anything else, and you can simply drop them from the equations, and the whole thing gets a lot simpler. So that leaves you eventually, once you've gone through this whole process, with exactly the Navier-Stokes equations as we had it before, but with an additional stress term on the right-hand side of the equation. Remember, we had the diffusion term, which was your fluid viscosity, molecular viscosity, multiplied by a gradient term. This term now becomes more complicated because you're now adding a Reynolds stress to that. The Reynolds stress is effectively the additional dissipation or diffusion that's due to all these small perturbations. So it's quite easy to visualize because the turbulent flow mixes things. So effectively your diffusion is much increased. So now you can simplify then your turbulence modeling approach by saying you're working with the variable viscosity version of the Navier-Stokes equations, but you're now using a turbulence model to give you those turbulent viscosities. So it's important to realize that the turbulent viscosity tends to be orders of magnitude larger than the laminar viscosity. In effect, you could almost disregard the effect of the laminar viscosity because it's completely dominated by the turbulent viscosity. But it's not constant. It varies with the level of turbulence. So where you've got a large degree of turbulence in the flow, then that effect is going to be very large. Turbulent viscosity is going to be very large, and it's going to decay to zero in areas where the flow is completely uniform. So if you've got a uniform laminar inflow of air, then the turbulent viscosity there will be close to zero. And then as it starts encountering disturbances, that turbulent viscosity is going to increase, and it increases dramatically, 1,000 times, 10,000 times, or even more. So this whole approach works reasonably well. It's got one very weak point, which is quite important. Well, it's got a couple of weak points, but the most important one is it's assuming that the turbulence is isotropic. In other words, that the perturbations will be more or less equivalent in all three directions. And mostly that's a reasonable approximation. It's not always true. And a classic example of where it's not true is a piece of equipment which you find very often in industry called a hydrocyclone, which is effectively a vertical cylinder into which you introduce a mixture of high density and low density things. It could be air and dust, or it could be different densities of gas, or different densities of fluid, or air with fluid in it. You introduce it tangentially and it swirls around, and the lighter substances go to the middle and the heavier substances go to the walls, and they drop out. Cyclone separators are used very, very widely. And it turns out that doing the CFD on a cyclone separator is extremely demanding, for the simple reason that the turbulence is very important and it's not isotropic. So then you can't get away with a simplified turbulence model. Righto, so let's just go take a look, without getting into any great detail, at a form of turbulence modeling. This is a one equation model that's widely used in aviation, in aircraft analysis. It's the Spalart-Allmaras turbulence model, and it solves for a single transport equation of the eddy viscosity. So you're not dealing with more higher level derivatives such as the turbulent kinetic energy. You're actually dealing with the turbulent viscosity itself. You assume an inflow boundary condition of very low turbulence viscosity, and then this gets amplified by gradients in the fluid, and it gets convected through the fluid. So once again, you've got yourself a transport equation that's of a similar form to the other transport or conservation equations we've had before. You've got a transient term, got a convection term, got a diffusion term, you've got some source terms. And it turns out with turbulence, of course, you now get some very large source terms, because the source terms are now picking up a lot of the effects of the gradients. So these make the equations nonlinear. You've immediately got terms that you can see in here that are nonlinear. So it's like everything else in fluid dynamics, it's nonlinear, but it's quite a lot more nonlinear. But this model has got a couple of advantages, and the one is that it's just a single transport equation, which makes it reasonably fast. It's got another advantage, which is that it works fairly well. So you, once again, primarily going to be using this with aircraft. Aircraft is streamlined. You don't have a lot of onset turbulence coming from somewhere else. So it's more important to take into account the effect of the turbulence that's generated in the immediate vicinity of the aircraft, close to the surface of the aircraft. And this has turned out to be particularly effective actually at predicting the flow separation on wings, fuselages, etc., which is one of the things that you'd really like to do with aircraft design. So the Spalart-Allmaras model has been an unexpected success. It's worked extremely well in the industry. And interestingly enough, it gets a second life when it gets combined with additional models that do resolve the eddies out in the flow field. We'll talk a bit about detached eddy simulation in a moment. Then you get into two equation models, and these models are the workhorses of CFD. This is where turbulence modeling first went effectively mainstream with the development of the K-epsilon turbulence model, which effectively says that you've got two things happening with the turbulence. You've got the turbulent kinetic energy, which is basically the generation of the turbulent effect. And then you've got a dissipation of that turbulence, which is epsilon. So you allow turbulence to be generated and you allow it to be dissipated. And the effective turbulence viscosity is a ratio of those two quantities. So once again, you've got transport equations, you've got transient terms, convection terms, diffusion terms, and then a whole lot of nonlinear source terms. And then quite a lot of empirical constants, and deriving these constants has been one of the big sort of developments in fluid dynamics, because a lot of them are not really theoretically derived. They have to be empirically calibrated, which gets you into the awkward situation that these models are not universally applicable. They work extremely well for certain types of flows. They can break down quite badly for other types of flows. And these models have been further developed. The K epsilon model was the original one. It was followed by models that try to address the shortcomings, such as the realizable K epsilon model and the renormalized normal group K epsilon model, which improved on a lot of the weaknesses and a few other things as well. And then a different family of methods, which is the K omega models, which basically solve not for epsilon, but a epsilon divided by K, a modified form of the turbulent dissipation. And this has also worked extremely well, but it's got its shortcomings. And then there's the shear stress transport equation model, which actually is a combination of the K epsilon model and the K omega family of models. This is a very, very large field. I don't really want to get into this in any great detail any further than what we've done already, because it is extremely specialized. Handle with care. This is where you need to read and find what other people are doing and what other people have applied with success. We've found, for example, that just like the Spalart-Allmaras model, the SST model is a very good general purpose model to use in the analysis of flight vehicles. We found, interestingly enough, that if you take the approach of applying the simplest possible turbulence model, we found that for a lot of higher Mach number flows, compressible flows, things tend to be dominated by shock waves. And then a very simple turbulence model is fine, because it's not the turbulence that's characterizing it. But if you take the special case of a body of a flight vehicle at a significant angle of attack, it's not dominated by wings and shocks anymore, then suddenly you need to pay a lot more attention to the turbulence modeling. Large eddy simulation. Large eddy simulation has become quite a big thing over the course of the last 20 years or so, largely because Reynolds average Navier-Stokes modeling is a non-physical assumption. You can get some pictures that look nice and even, but actually they're very inaccurate. The effect is not on time average is not too bad, but there's quite a lot that you can lose in terms of trying to understand what's happening with the fluid dynamics. So large eddy simulation is an attempt to resolve some of this. And this came originally from research into atmospheric flows, because as you know from watching weather charts, large eddies, swirling masses of atmospheric air, got tremendous effect on the weather that we actually experience. So large eddy simulation became originally a thing in the modeling of atmospheric flows, and it became an issue in modeling normal fluid dynamics as well. The basic approach is that you've got turbulence on various scales of length. If you've got large eddies, which are significantly larger than your grid resolution, then you can easily resolve them within basically a transient Navier-Stokes simulation. But there's stuff that happens at smaller than grid scale that is still important. So you end up having to combine this large eddy, which is really just unsteady Navier-Stokes, with what's happening with turbulence modeling on what's happening at subgrid scale. LES works, but it actually turns out to be extremely expensive, and there's a subtle reason for this, and it's got to do with mesh resolution. Everything that's below mesh resolution as handled by the model, and everything above it obviously is explicitly solved. But it means that if you change your mesh spacing, the size of your mesh, then it completely changes the turbulence situation as well. So you have to basically have small grid cells more or less everywhere. And it becomes extremely expensive when you get into boundary layers, because the assumption in shear layers near the wall is that there's not much happening normal to the wall surface. Everything happens in terms of gradients across the boundary layer. And you can resolve that nicely with your computational mesh by having very fine spacing next to the wall in the direction normal to the wall, but quite large spacing parallel to the wall. But if you were trying to take that approach with large eddy simulation, you would completely lose all that effect, because you've got now different length scales for your different directions. So you have to end up with very fine isotropic meshes to capture large eddy simulation effectively. And that makes it very expensive simply because your meshes are very large. So that's led to the development of better techniques such as detached eddy simulation, we'll talk about in a moment. But if you're talking about planetary scales, this is research done on the hardware at the Center for High Performance Computing. Over the lifetime of the CHPC, our biggest single use of the computing capacity has been this particular research group, which is the Southern Ocean Carbon Climate Observatory. The Southern Ocean, southern part of the globe, is a very large part of the world's oceans, but it's quite poorly studied because it's a long, long way away from most people. But it turns out to be extremely important when it comes to absorbing carbon from the atmosphere. So obviously, we get into the climate change situation to try and understand what's happening. We need to understand what's happening in the Southern Ocean. So one of the areas that's been researched has been to model the ocean currents in the Southern Ocean at sufficiently high resolution that you can actually capture these large eddies. And it gets surprisingly complicated. You'd like to think of ocean currents as things that go down this coast and up that coast and up that coast and down this coast again. But it actually turns out to be a lot more complicated, with lots of vortices and eddies and various forms of mixing. And in fact, the vertical mixing is turning out to be even more complicated, where the effect of turbulence in the ocean has got an enormous effect in how the upper layers of the ocean get mixed. So this is your area where you don't have a high resolution model, and where everything is done essentially with subgrid scale modeling. So you're modeling the effect of turbulence at subgrid scale. But here you're actually resolving with a much finer grid the formation of these eddies. And it turns out to be a crucial part of understanding what's happening in that ocean. So the more sophisticated method that has become a bit of a workhorse is detached eddy simulation, which is a hybrid method again. So large eddy simulation is basically purely based on the size of the grid cells. Anything below the mesh cell size is dealt with models, and everything above it is resolved. But it means that your boundary layers, your near wall regions, become very expensive. If you stay with Reynolds average to Navier-Stokes modeling near the walls, but resolve the eddies away from the walls, you find a much more efficient way of capturing what's happening in your flow. And you can find that you can use a relatively simple method, Rand's turbulence model in that region near the wall, as long as you're capturing your larger eddies away from the wall with detached eddy simulations. This is another application where the Spalart-Allmaras model has become quite effective. So this is just a YouTube video, so it'll take a moment to load. So this is a V-shaped obstruction in a channel subjected to a uniform flow, and then the flow is simulated with a detached eddy simulation. So this rather shows you the strength of the method. If you were to follow a Reynolds average Navier-Stokes approximation, all that you would get in this region would be a kind of a diffuse area of mixed flow. But in practice, there's an enormous amount of structure and complexity happening there, and it may be important to know more about that. Right, so to summarize here, as I said, I was a little bit uncertain about whether one should introduce turbulence at this stage of the lectures because it is such an extremely complex field. But if you want to use CFD reliably, you've got to understand that turbulence is there and it needs a lot of attention. If we didn't have turbulence, CFD would be a lot simpler. However, there are times, and I've basically described the ones, for example, low speeds, or by contrast, speeds where things are dominated by shock waves, for example. The answers may not be strongly determined by turbulence. You may only need to have a turbulence model in your equations simply to keep the model stable, because you can't get laminar flow at high Reynolds numbers, so you need something to do the turbulence. But actually the answers are being determined by something else, by geometry, shock waves, something else. But then there are other cases, and the hydrocyclone is a classic one, where the turbulence is extremely important and you have to pay special attention to that. So you really have to make a point of questioning your own assumptions here. Okay, I'll stop that there. Questions. I'm going to start picking on people here.
We found it to be quite effective.
What, to pick on people?
We were not as kind as you were.
With
the Python course.
Yes, but you see, I think you had assignments to hand in at the end of the Python course. We're not going to do that here.
No.
Okay, so if I may ask a question, is everybody asleep? Okay, evidently they are. Shall we just stop everything here? Okay, Solomon van Niekerk says he's not asleep, but do you have a question to ask? No.
Maybe that's the answer to the question if they're asleep, not to the answer to
Okay.
the question if they have questions.
I'm really happy that you're not asleep. Yeah, this is not easy stuff to get across in a way that will keep people interested, but unfortunately it's necessary to know about it. Right. Shall we move on to the third part of this lecture then? And this is a very short piece, but we'll talk a little bit about the individual slides. Okay, peculiarities of CFD. And I think this is where CFD rather distinguishes itself from some of the other computational methods in the sense that it needed a lot of tricks to become possible. It's not unique in that sense. I think it's been quite surprising to see how long it's taken for particle simulations, particle motion simulations to go mainstream. These are very important. In other words, if you discharging coal from a large hopper into a truck or a conveyor belt or so, it's quite important to know what it's doing, and it's difficult to do right. And these methods have only now started becoming mainstream. So they've trailed CFD largely because they've got even more peculiarities than CFD. But CFD trailed a lot of other methods, such as simulation of nuclear reactions, and certainly structural analysis. Structural analysis was mainstream a long time before, numerical structural analysis was mainstream a long time before computational fluid dynamics started moving from the research space. It's got a lot to do with some of the peculiarities of CFD. Well, I think there's been a question in the comment in the chat box there, which I think is very valid. We need the codes and exercise to understand the simulation better, and I think that's right. This is priming you to get into actually doing something with the CFD code, which is why I'm giving you the voluntary assignment of doing some work with OpenFOAM. Okay, so Mteto is asking quite a loaded question, which is, have CFD methods been used effectively for numerical modeling of the atmosphere? If not, why? That is a big question, because there's more similarities between CFD and atmospheric modeling than there are differences. Effectively using the same equations, using the same computers, using the same computer languages. But there's surprisingly little crossover. And I think it's got to do with the fact that these are both very specialized sciences. So people and research groups have tended to specialize in them. And one of the things which the people in the CFD world shake their heads in disbelief about the atmospheric simulation people is that all atmospheric simulations are still done with structured meshes. For a long time, with basically meshes that looked a lot like longitude and latitude lines, which introduced all sorts of problems because the longitude lines all converge at the poles, which give you a rather awkwardly shaped numerics going towards the poles. Some of the numerical methods have translated, such as solving large systems of linear equations. But up to now, the biggest single separation point has been that that fluid dynamics moved to unstructured meshes to deal with complicated geometry a long time ago, 20 years or more. Whereas atmospheric modeling has tended to stay with structured meshes, which have got certain advantages, because the Earth is, to first approximation, a sphere. And it's fairly easy to model the Earth with a structured grid. And when you've got structured grids, there's certain advantages to the numerics. So it hasn't been a compelling reason to move to unstructured meshes for the atmospheric flows. But there was a movement within the CSIR a few years ago to try and bring these groups closer together, but it didn't actually go anywhere because they're so far apart already. Also, the scales are just completely different. In fluid dynamics, we're talking about turbulence models that deal with things on a very small scale. In atmospheric model, you're talking with things that deal on scales of kilometers. So your parameterization of your subgrid environment is completely different, simply because you've got so much more happening at the subgrid scale in atmospheric flows. I think it's perhaps the single biggest difference. There's so much more that you need to parameterize. Would it be possible to model the effect of turbulent flow between wind turbines within a wind farm? Oh, yes. That's where you actually that's where you're getting into the point where you're on the boundary between atmospheric flows and CFD. So you would typically need your atmospheric models to give you your wind that's arriving at a wind farm. But then you need to move to CFD methods to take that velocity field and model its distortion by the individual wind turbines. And of course, this is huge because wind turbines are very, very large and they extract a large amount of energy from the atmospheric flow. So you need very large turbulence models, and you need models with eddy simulation because these wind turbines are very unsteady and they're shedding vortices, and it's important to model the mixing effect of those vortices and how they impinge on the other wind turbines in the array of wind turbines. So this is where the two methods clash very, very effectively. They need to be combined because the wind's got to come from somewhere, and then the effects on the individual turbines on each other and the immediate topography is beyond what you can do with atmospheric models. But there's a third class of codes here, which is the ones that are actually used for designing wind farms, which take a lot of this into account, perhaps not at the very small level of detail. But yeah, that is where the two fields meet very effectively. Right, some of the peculiarities of CFD. How can we calculate the computational expenses for a numerical model? I think we'll have to get back to that one. Oh, needed RAM. Yes, that's a good question. I'll get into this a little bit later on Friday's lecture when we start talking about structured and unstructured solvers and coupled and uncoupled solvers. You can, to a very first approximation, assume that 1 million CFD cells will need a gigabyte of RAM. That's a heuristic. That's a very loose thumbsuck, which is dependent on a lot of things. I've worked with methods that used far less memory than that, but I've also worked with methods that needed a lot more than that, and that's without taking into account other effects. If you've got more complicated turbulence models, you need more memory. If you're solving energy equations, you need more memory. But yes, somewhere in the region of 1 to 4 gigabytes per million computational cells is a reasonable number. But there's a lot that goes into that assumption, because some methods, like for example, tetrahedral grids, have got far fewer grid points per cell, so they need less memory. Whereas the modern trend towards polyhedral cells, think of, well, in cross section, it looks like a hexagon. If you're actually going to sketch out your computational cells, they might have n number of faces. They could have 12 or 15 faces. They've got a lot of grid points per cell, and they need a lot more memory. But think in terms of 1 to 4 gigabytes per million cells. It used to be a big constraint. We don't worry about that anymore. It's a relevant question for us when we are drawing up specifications for a new computing system for CHPC. How much RAM do we need per core in the cluster? So we think in terms of around 2 gigabytes of RAM per core, and it turns out that's way more than we need for CFD. CFD, you need far less than that, but actually it's quite difficult to get memory modules that are smaller than that. Get back to this lecture. The long road from partial differential equations to practical general solutions. We've got a lot of non-linearity. The turbulence models are non-linear. The momentum equations are non-linear. So you're always going to need iterative solutions. If you're dealing with structures, for example, you're dealing with things which, yeah, they can go non-linear when you start getting plastic deformation, or you get contact or fracture or that kind of thing. But if you're dealing with simple structures, Hooke's law, it's all linear. So fluid dynamics is different there because you inherently have to have iterative solutions to deal with the non-linearity. We can do a lot with steady state solutions, but in practice, flow is never steady. So the more fidelity you want from a solution, the more use you have to make of transient methods, because fluid dynamics is inherently unsteady due to the turbulence and others. We've talked about the pressure velocity coupling. You need special techniques. There are several special techniques that you can use, but by default, you can't simply follow a sequential solution of the equation. It's not going to work because you don't have an equation for solving the pressure. And then it turns out that you need very large computational domains. If you're doing structures, you only need to model the thing that you're interested in the structure. If you're dealing with fluid dynamics, you have to build a computational domain that's a large region that encompasses all the fluid around the thing that you may be interested in. I'll show you on the next slide. Geometric complexity and how geometry is defined. This is a very, very specialized field. If you're working with research methods, this doesn't seem like a question at all. You know, geometry is what it is. When you're dealing with industrial use of these methods, you find that you're getting geometry from computer-aided design methods. And guess what? They define geometry in different ways, and they don't always agree with each other. And then again, these models have got lots and lots of details. Do you need to model the slots on the screws? Do you need to handle the door handles on a building? What is a flaw in the geometry? In other words, where the models are just bad. And believe me, that happens all the time. What is so small you don't need to worry about it? But what do you get that's so small but actually needs to be taken into account? So what's the difference between a feature and a flaw? That's a part of what needs to be taken into account with the development of CFD or use of CFD. We've seen DNS, direct numerical simulation, is really relevant for research purposes only, scientific research purposes only. And then turbulence, which introduces trouble at all sorts of levels. Okay. Yeah.
There's just
Now,
a
let's get
question.
into it. I'm looking at that question, trying to figure out how I'm going to ignore it.
Okay, can I write the answer to it?
Please do. Okay, so Andrew will handle that question. Thanks very much. Because it's getting into a bit more detail than we can easily handle in the lecture here. Right. Large computational domains and spatial resolution. So this is a typical C-shaped grid around an airfoil, a symmetrical wing. At the kind of resolutions that you would use in real life. In fact, your domain is so large that you cannot even see the little wing in the center. So NASA recommends, if you're doing aerodynamics work, that the boundaries of your computational domains should be at least 100 chord lengths away from the body of interest. So the influence of the boundary on the surface of interest obviously decays asymptotically with difference. So you may be able to get quite good answers if you only go 5 chord lengths away. But to get to the point where you've definitely got no influence, you've got to go as far as 100 chord lengths. And if you're following these recommendations very strictly, you end up with very, very large domains. There's an additional thing that comes in here. The person who generated this mesh went to a lot of trouble to keep these grid lines crossing each other orthogonally, which improves the numerics of the discretized equations, which is a very, very nice feature to see. But then also the mesh gets so fine at this scale that we cannot even distinguish the individual mesh lines when you get close to the surface. And it turns out that if you're interested in what's happening in the immediate wall region of this body, you need to mesh down to extremely, extremely fine levels of spacing normal to the surface. This is related to viscous effects and turbulence models. There are 2 main families of approaches here. One is to use your boundary layer methods to develop an approximation of what the velocity and turbulence is going to be doing in the region close to the wall. And instead of trying to solve your turbulence equations all the way up to the wall surface, you can follow the law of the wall, which basically fits a curve to it. We use wall functions. And in real life, you'll try to use wall functions wherever you possibly can. You still need very fine wall spacing, but basically you're lumping the lower layers of the boundary layer together and using a subgrid scale approximation to what's happening there. Even then, to get into the regions where these wall functions are calibrated, you need to get into a region where the distance from the wall expressed as a non-dimensional boundary layer parameter is of a y plus value of around 30 to no more than about 200. That depends on the flow. It's a special, it's a way of expressing where you are in your boundary layer. Physically, when you're dealing with wings at general kind of speeds and things, it means that that first layer of the grid has got to be as thin as about 0.3 of a millimeter. So you think about how thin 0.3 of a millimeter is. It's basically 3 sheets of paper. That's how, about this big as you can make your first grid cell in terms of height away from the surface. And it turns out that there's a lot of approximations in that method, and it's not hugely accurate. If you're dealing with airflows and you want on wings and you want to resolve them accurately with a turbulence model, you actually need to fit that first grid cell into the laminar sublayer. So the very inner part of the boundary layer. And that is a y plus value of around 1. So those of us who've worked with this become accustomed to meshing entire aircraft geometries with that kind of wall spacing. But it's bizarre when you see it the first time, because on typical sizes, that means that that first layer is in the region of 1 micron to 10 microns. So it's extremely small. The problem why this is necessary is that you're getting into the layer of the inner layer of the boundary layer, which is laminar, and the only things that count there are molecular viscosity. So we don't go down to the size of molecules mercifully, but you need to get right into that laminar sublayer, which is that thin. So yes, think in terms of 1 to 10 microns as a wall spacing, but in fact you could be in your far field boundary 100 or 200 meters away from that body. So you're talking about length scales that vary from hundreds of meters down to 1 micron, 10 micron. So from a numerical methods point of view, that's very demanding because of the great difference in sizes that you need to accommodate. Okay, let's move on to the next one. Geometric precision. This is a very simple, very simple example of the kind of thing that you're dealing with. But it's related to the reality of computer-aided design models. Computer-aided design models, CAD models, handle curved surfaces with non-uniform rational B-splines. They interpolate the surfaces. So you get smooth surfaces, but they're not precisely expressed. And the way that the different codes express these things, the way it's been implemented, is not always the same. So by the time you get a CAD model from the CAD design office, you bring it into your pre-processing software for your CFD method, you may find that surfaces overlap, or they fold, or they cut each other where they shouldn't do so. And you cannot do the CFD analysis until you resolve all these difficulties. It's a very labor-intensive task. There's quite a lot of tools that you can get to help you now. The best possible tool is to take control of the geometry yourself so that you can do your CAD model with the intention of modeling the geometry consistently and accurately. In a design office of any nature, it could be architecture, it could be mechanical, it could be electronic, whatever. Your main purpose of the CAD model is to do a layout, and then to be able to generate shop drawings automatically and to provide the organization with a bill of materials. It's not primarily there to get your precision. So the worst models I've seen are the ones that come from architects, because architects have got their special CAD models, CAD software with all sorts of special models built into them, so they can easily do double glazed windows, toilets with handles, sliding doors with handles, and all that. When you're trying to do an aerodynamic study of the ventilation or the external flow of that building, all of that is information you don't need. But in order to build an accurate CFD model, you need to handle all those little bits of geometry and resolve all the conflicts and things. One of the salesmen of a company that sells software for building grids for CFD has made the rather bold statement that the cost of dealing with geometric difficulty per year exceeds the total market capitalization cost of the entire computer-aided engineering industry. In other words, dealing with geometric problems is one of the main functions of your practicing CFD engineer. In the research environment, where most of you are aiming to be for the next few years at least, generally speaking, you don't have to worry about that because you've got control over your own geometry, and you can very often specify your geometry parametrically. You don't have to deal with this. Once you start dealing with industry problems, this becomes a very dominant part of the job. There's an interesting side point here to the question of what is a curved surface actually? Because the B-spline interpolated approach to modeling surfaces is somewhat imprecise, or it can be somewhat imprecise, a lot of the tools used in generating grids for CFD methods use a faceted approach. Faceted, in other words, it's built up from triangles. A typical file format that's used is a stereolithography format, which is used for additive manufacturing or 3D printing. And basically, it breaks up any surface into triangles. Triangles are nice to work with because 3 points always lie in a plane, and you can make sure that adjacent triangles share 2 points, which means that they share the same edge, which means that they're waterproof. That's why it gets used for additive manufacturing. And all that's lovely. The problem with a faceted approach to things is it's not smooth. So this is a CFD simulation over a very simple body, subjected to a very simple flow. It's a smooth body. It was designed in CAD software to be a very smooth body. But when you look at the CFD solution, it looks like a zebra. It's got these bands of alternating pressure. Why is that happening? It's happening because the meshing software has broken up this very smooth surface into facets. That's the geometry part of it. That's before it actually turns it even into a grid. So the underlying geometry is already non-smooth. Because the underlying geometry is non-smooth, you get a non-smooth solution. May or may not be important, but it certainly doesn't look very nice. Right, to wind up today's lecture, the steps along the road of dealing with CFD solutions can be summarized with the following. You have to have a domain around the thing that you're interested in. Could be that you're dealing with an internal flow. It doesn't change anything. You've got a domain, a collection of grid cells, certainly a body of fluid or a body of solid. And that has to be discretized in the form of meshing. So different ways of meshing it. You can do it with Cartesian meshing, curvilinear meshing. You can use multiple blocks of multiple curvilinear blocks. We'll talk about that in the next lecture, and I'll show some of this next week. Or you can use unstructured polyhedral, tetrahedral, cut cell meshing. There are different ways of meshing the domain, and this relates to a question that came up on Monday, which is what is the best element to use? And it turns out the best element to use is there's no simple answer to the question, because it's amongst other things related to whether using finite volume or finite element approximation to the problem, and also what the geometry looks like. So one of the real life difficulties is that objects in real life have topology. By topology, I mean people have bodies and they've got arms. Aircraft have got bodies which are long and round, and they've got wings which are long in a different direction. And isotropic meshing, when you're dealing with bodies that have topology, is very inefficient because your spacing tends to be the same in every direction, but things don't vary the same in every direction. There's a lot to meshing. It's a big field. But that's the first step along the road towards getting workable CFD solutions. And the next is to take your partial differential equation and turn it into a set of algebraic equations. And this is where we come into finite difference, finite element, and finite volume approximations to going from differential equations to algebraic equations. And then you've got to interpolate between the various grid points in your solution. Once again, the different schemes lead you towards different methods, but your choices here are quite important. Talk about that more on Friday. And then you need to couple the equation. You've got to find some way of resolving this question of the fact that the pressure is coupling the equations, but the pressure is not necessarily in a separate equation. There are segregated and coupled methods of dealing with this. And then you have to solve all those equations with some form of equation solver. Once again, we'll get into that in a bit more detail on Friday. This is not even talking about the fact that you've got to deal with basically an initial value in a boundary condition problem. Your domain starts off at some initial condition, which you've got to get from somewhere. Most often that's not so important because you're heading somewhere and it's where you end up and not the starting point that is important, but the starting point could be important. But then of course, very important is you have to specify the right type of boundary conditions and the right value of boundary conditions. Okay, that's it for today. Any more questions to be asked? So I see Jack's asking, is it often that we're going to come across answers that aren't accurate but still useful? I've noticed that as a trend towards the beginning of slides 2.2, like laminar flow. Yes, that's life. How accurate is accurate enough? There's a difference between science and engineering. In fundamental science, you are trying to find what is. In engineering, you're trying to answer the question, what can you do with it? So already you've got two different approaches there. The important thing is to know what you're trying to do with the results. It's extremely expensive to always try to get answers that are to a high degree of accuracy. It may be so expensive that you can't generate enough of them. I like to follow the approach that if you're dealing with the industrial environment and you're doing modeling and simulation in a product development environment, for example, you're going to follow a trend of escalating precision. You want to start off coarse to explore a large design space. You're trying to rank alternative options, pick the ones that are more likely to work. As you proceed along the development process, you're going to try and refine your answers to make more accurate predictions about whether you're going to meet your performance, whether you're going to meet your performance targets. So it's always important to bear in mind the question of fit for purpose. What are you going to be using results for? And I think you should always just remember there's no such thing as 100% accurate. There's always, unless you're dealing with integer algebra, everything else in life is got a certain level of precision associated with it. Some levels of precision are extremely, extremely high. Others are quite coarse. It depends on what you're dealing with. So there's degrees of accuracy, and there's always degrees of doing simulation work, what you're trying to achieve with it. It's been a disconcerting trend that I've seen in education of and training of people to work with simulation methods, that ultimate accuracy is basically regarded as the only objective. And that's not appropriate, because 100 approximate answers will probably get you a better product than a single precise answer, depending on what size, what stage of your development you're dealing with. You always, with any form of simulation or calculation, need to apply appropriate quality control. So even if you're doing fairly imprecise modeling, basically painting with a broad brush, you've got to know how broad that brush is and how far you're going over the edges if you want to push the metaphor that far. If you're trying to certify a product that people's lives are going to depend on, you need to know how precise your answers are. So at any stage of any method, you need some level of appropriate quality control, but that particular level and method of quality control depends on what you're trying to do. Any more questions?
Please, let's try another system. What about if we offer 100 Rand book voucher to the first person who asks a question?
Not all at once, will you?
I said just the first one.
I hope you've got book vouchers, Francesca.
Yeah, no, we'll make a plan. Okay, here it comes. Kylan Reddy, you're the winner.
Okay, so you'll make a note of that, Francesca. Right.
Let's do the first. Sorry, just to let me send them. Kylan, please, can you post in the chat your email address so that we can make a plan?
Yes,
I know that I can find it, but just for the ease of having it there. Please put, fantastic. Thank you very much.
Okay, so yes, there are lots of applications because in some ways people are fluid dynamic machines. You've got fluids digesting your food in your digestive system. You're breathing in a gas in the form of oxygen and nitrogen. You're exhaling carbon dioxide and all sorts of other gases, and that lot gets diffused into your blood, which is blood's a special case of a fluid because it's a nasty fluid. It's a non-Newtonian fluid. The viscosity is dependent on the rate of on the shear rate, so you cannot assume the viscosity is constant. So it's a very involved field, like all these are. One of the more interesting groups that I am aware of, which is what you were asking, is at the University of Cape Town. The researcher involved there is Malebogo Ngoepe, And they've been doing some very, very interesting CFD work on aneurysms. In other words, where you get these little bits of vessels, blood vessels, bulging off, forming almost separate but connected regions or chambers in your vasculatory system. And now you've got blood flowing past this and also partly into these aneurysms, and then the blood starts clotting. So they've done some very good work on actually building a clotting model, so a numerical model which approximates the way that the blood is going to form a clot in that aneurysm. And then your big thing you don't want happening with an aneurysm is you don't want that clot being released, because once that clot gets released and gets into your bloodstream, you're probably going to die, or you're going to have a very, very bad time. So it's quite an important thing to model correctly. And they've done some very, very interesting and very good developments. So that's Malebogo Nwope at, let me just type her name there. She's a lecturer at the University of Cape Town, and really some very, very interesting work being done there. Now, the CHPC was supporting that research project for a while. The other lecturer at UCT involved with biomedical engineering is Thomas France. So if you're looking for somewhere to go and to study in biomedical engineering, you could get in touch there, because actually while we were supporting that research program, we had a lot of difficulty actually finding postgraduate students who were interested in doing master's or PhD thesis there. Right. Okay, so how do you decide the more convenient technique for your simulation, the finite volume or finite element or something else? Well, I think you would generally approach it in another way, because you're not going to sit down and write a finite element or a finite volume code at this stage. These methods have been developed. These methods have had thousands of man-years that have gone into the development. So even if you're wanting to develop a special solver, you would be doing it within the framework of a finite volume method or a finite element method. We'll talk a little bit more about the difference between the methods on Friday. You can do fluids with finite element methods. You can do structures with finite volume methods, and people have done that. What is interesting is nobody seems to be actually doing it in practice. There are very few commercially used fluid dynamics finite element methods. They exist, but they don't have anywhere near the kind of market penetration that the finite volume methods have got. And the opposite thing happens with structures. Where it gets messy is in between, for example, heat conduction. Heat conduction falls right in the middle between whether it's more convenient to do with finite element or finite volume. With finite volume, the main thing is you get inherently you get conservation of your properties, and you're solving conservation equations here. So the finite volume methods are particularly well suited to fluid dynamics, but maybe there's also just a lot of history involved here. There's thousands of man-years involved in the development of appropriate techniques for their applications for finite element and finite volume methods. And switching between the two just because you can is not a particularly useful exercise. Okay, anybody else? Okay, well, we shall meet again on Friday then.
Yeah, and thank you very much, Charles. It was again an excellent lecture. Thank you very much. And please don't forget the participants that we meet again at 2. Yeah, and there will be again Morten speaking about machine learning methods. Yeah, so please don't forget that, and encourage others that are not here this morning to join us in the afternoon as well. And maybe we will offer another voucher for question this afternoon. I will just need to do some sums to see what our budget permits, but let's do that again this afternoon. And remind me if I should forget. So Charles, again, thank you very much for the, sorry, I see there is a raised hand. Uchenna, please, If you would like to speak, just ask your question. Sorry, the question, Charles, is in the chat.
Okay, is there any situation where K epsilon model works better than K omega in aerodynamics? Okay, so yes, there is. And this is where the difficulty with the classic K omega model is it's unusually sensitive to the inlet boundary conditions, which are very often not very well known. So generally speaking, in aerodynamics, you set your inlet turbulence values very low because they are very low. You're not going to be flying an aircraft in conditions that are extremely turbulent on the kind of scales that we talk, the aircraft scales that we're talking about here. So it's quite awkward having a method where the answers are dependent on the inlet boundary condition, where the inlet boundary condition cannot be known to any great extent. So that kind of breaks down with the K omega model. The K epsilon model is nowhere near as good as predicting the aerodynamics, but it is not so sensitive to the inlet boundary conditions. So that led to the development of the SST model, the shear stress transport model. The shear stress transport model uses the K epsilon model away from the wall regions. So in effect, it gets you away from that inlet boundary condition problem, but it transitions gradually to the K omega model in the regions near the wall, which gets you the improved accuracy of the K omega model in that region close to the wall. So that's how it's handled in practice. When we were doing applied aerodynamics in the days before we really had the SST model working, we found that flows with shock waves was fine. You just didn't worry about the turbulence because everything was so dominated by the separation caused by the shock waves. But in general, the SST model has turned out to be an answer to that. You don't want to look at the answers too closely. I've done that, and you find that you get a large region of flow where the turbulent viscosity is extremely low, and then at a geometric distance from the boundary where it transitions to the K omega model, you get a sudden jump in turbulent viscosity, which is so non-physical, it's not true. The saving grace is because it's away from the boundary, from the surface, the walls. It doesn't seem to affect the answers, but it's a tremendous artifact and really shouldn't be there. But it works in practice, which is why you always need somewhere to check your answers and correlate your answers and pull things together, all your different experimental and numerical techniques that you're using. Okay, we've gone quite a lot over time, Francesco. Shall we call it off here?
Yeah, no, I guess this is the good time to stop for this morning, and I'm really pleased that we managed to get more interesting questions out of the participants. So Charles, thank you very much for making it interesting, and thank you for the participants for being active this morning, and also a big thank you to Andrew and Ilya for being with us this morning. And I see also Benjamin is here. For the moral support. Thank you very much.
Okay, see you guys Friday.
Thank you. See you at 2 o'clock. Yeah, bye.
Bye-bye.
Bye.